Hello everyone, my name is Rishabh and in this video we are going to discuss about the problems with RNN. RNN. We all know this were the major breakthrough in the field of deep learning. Why? Because they have introduced one special ability that can process the sequential data. And the ability was to retain the memory. They can retain the memory along the sequences. That was the great innovation. Now despite this great innovation, they faces some serious challenges. The challenges were majorly vanishing gradient and the exploding gradient that we are going to discuss in this video. Now, understanding these challenges are so crucial because this will pave our way to understand the newer architectures which are LSTMs and the transformers. So, I hope this video will be useful to you. Let's jump into it.
In this video, we are going to discuss two major problems with RNN. Those are vanishing gradient problem and exploding gradient problem. Let's understand in detail about the vanishing gradient problem first. This vanishing gradient problem arises because of long-term dependency in our sequences. What do I mean by long-term dependency? Let's understand this with the help of an example. The example which we are going to take is next word predictor. And let's assume that this next word predictor is using a RNN based model to predict the output. So when I pass this sentence, this sequence as an input to our RNN, then that RNN will predict the word that will come after this sequence. A word that will be contextually good fit for this sentence. So that RNN will give us the output, say ML. Python is popular for ML. We can clearly see that this ML is contextually good fit for this sentence. Or this ML is contextually dependent on Python. What do I mean by contextually dependent? Say, instead of Python, if I have JavaScript in this place, and if I pass this sentence, JavaScript is popular for, to our RNN, then that RNN would have given us the output instead of ML, WebDev. That is, JavaScript is popular for WebDev. So this is what I mean when I say contextually dependent. So this ML is contextually dependent on Python. So this type of dependency is called as short-term dependency. Why? Because this ML and Python are just 3 timestamps apart. 1, 2, 3. Only 3 timestamps apart. That is the reason why they are called as short-term dependency. So this is short-term dependency. Then this will be long-term dependency, which we are going to see now. This is long-term dependency. So what happens in long-term dependency? Say, if I pass this whole sentence one by one, that is, timestamp t equals to 1, I'm going to pass this. T equals to 2, I'm going to pass this. 3, 4, like this. I'm going to pass this whole sentence as an input to our RNN. What is the sentence? The sentence is Python is a programming language. It is one of the fastest growing programming language ... It is popular for. I want a word that will come after this. It is popular for. I want a word in this place that will be contextually correct in this sentence. So when I pass this input to our RNN, the RNN fails to give us the contextually correct output. Why is it so? Because here we can clearly see what we want. We want a word after this it is popular for, right? And this here, this it refers to Python. This we know that this it refers to Python. But RNN does not know that this it refers to Python. Why? Because RNN has one problem. RNN has a problem of forgetting the memory of the earlier timestamp in our longer sequences. So RNN will forget about the earlier timestamp, these things. In a longer sequences, RNN will forget the memory of earlier timestamp. So RNN will not know that it refers to Python, and that is the reason why it will not be able to predict the contextually correct word that will come after this sentence. So why is it happening? Why RNN is forgetting the memory of the earlier timestamp? Now this will be interesting thing to explore upon. Let's dive into it. So to understand why RNN was forgetting the memory of the earlier timestamp in the longer sequences, we first need to take a short look on the forward and the backward propagation, which we have discussed in our previous videos. In forward propagation, what happened? We provide an input, say x1 at timestamp t equals to 1. We get one hidden state h1. That hidden state h1 is again passed at timestamp t equals to 2 with another input x2. They both will together make us an hidden state h2, which we are again going to pass in the forward timestamp with different input x3, and we are going to get output like this. And when we apply the activation function, say sigmoid, in this output, we will get y cap. What is this y cap? This y cap is the predicted value. And suppose we are dealing with supervised learning, so y will be given to us, which is actual value. So we have y cap. Next step will be to calculate the loss, which is this one. One thing to note here, that this loss is the binary cross entropy loss, which we have seen for the example of sentiment analysis in our previous videos. But in this case of the next word predictor, the loss will be categorical cross entropy loss. So formula will be different. But our main focus is not on the formulas. Our main focus is on the concept of the process, what's happening in the forward and the backward propagation. So this is the loss which we have seen. So the next step in any deep learning journey will be to minimize the loss. Will be to minimize this loss. And if you remember, we have taken gradient descent as one of our approaches to minimize the loss. In gradient descent, what happens? We find the optimal value for Wi, Wh and Wo. We find that optimal value for these parameters such that our loss becomes minimum. That is, we need to find the optimal values for these weights for these parameters. How to find it? We have to apply the formula of gradient descent, which is this one. The formula of gradient descent, which is the weight updation formula. So here, what happened? These are the initial weights, which will be random for the first sentence. These are the learning rates, which will be given to us. The only thing which we need to find to do the weight updation, to find the weights, is to calculate this derivative. And we have seen in our backpropagation videos that we can calculate this derivative using backpropagation. We will apply backpropagation and we will find this derivative one by one. So these are the equation which we have got for this derivatives. This is change in loss with respect to change in output weight. This is change in loss with respect to change in input weight. This is change in loss with respect to change in hidden weight. So by doing the backpropagation, we have successfully found the derivative or the gradients of these three. Here if you can see, these two are in the general form because they have summation in it. So their original equation somewhat looks like this. This is the original equation which I have taken for this second derivative, which is dl by dwi. If you can see, this equation is having three terms. First term is this, second term is this, and third term is this. Why this equation is having three terms? Let's see with the help of an architecture. This is the architecture of our RNN, and let's see, at first let's see what does this dl by dwi represent. it represents change in loss by changing Wi, which is input weight. And in our RNN, where we are having 3 inputs, we can clearly see we will be having 3 input weights also. That means this will be O, this will be loss y cap, and this like this. So if we need to find change in loss with respect to change in Wi, then we can have 3 paths. The paths will look somewhat like this. For the first term, the path will look somewhat like this. Change in loss will cause change in loss can be done by using change in y cap. Change in y cap can be done using change in O or change in H3. Change in H3 can be done using change in Wi. So you can see, just I have to do this 3 parameters changing, and I can do the change of dl by dwi for this term. That is, this one represent the change in wi with respect to the input x3. Similarly, for this term represent this term, the path will be change in L, change in y cap, then H3, then H2, then wi. You can clearly see this term has H2, so that is why this path it will follow. And this term represent the, with respect change in L with respect to change in weighted input of x2. Similarly, this one represent for x3. Sorry, this one represent for x1. Now, if you see carefully, there are some similarities in these 3 terms. Those are, this term is similar in all these 3 equations, right? So we can name it as C. Okay. Now we just need to find the derivative of the hidden states, which is this one. We just need to find the values of the derivatives of the remaining hidden states. In forward propagation video, we have already discussed that we have already derived the hidden state formulas, which look somewhat like this. Here, all the hidden state is in the function of tan h. That is, tan h of somewhat input. So we know this tan h, the value lies between -1 to 1. But what we want the value for derivative of hidden state. That is, we want the value for derivative of tan h. The derivative of tan h lies between 0 to 1. For this example, let's take a constant value which is 0.7 for every hidden state derivative. For every h1, h2, h2 derivative, let's consider it as 0.7. So what will be the value for this first term? The value for this first term will be C multiplied with 0.7, because we have only one hidden state derivative. For the second one, it becomes C into 0.7 into 0.7, which is 0.49C. In the third one, it becomes C into 0.7, it becomes 0.343C. So what does this values represent? What does this values represent? This values represent the contribution of their respective input in predicting the outcome. This 0.7 represent the contribution of x3 in predicting the outcome. This 0.49 represent the contribution of x2 in predicting the outcome. So here, can you see some interesting observation out here? If you carefully see, then the contribution is decreasing as we move to the older timestamp or for the older inputs. This x1 is what? This x1 is the older or earlier input. This x3 is the recent input. See, this x3 is the recent input. This x1 is the older input. And as we move to the older or earlier input, the contribution of that input in predicting the outcome decreases. In this case, where we are having 3 timestamp, that is 3 inputs, the decrease in the contribution is not that much. It's still decreasing, but it's not that much. So the output contribution of each of the input will be significant. But what happens when we have timestamp, say t equals to 100, when we have timestamp till t equals to 100. That is, we are having a sequence where 100 words are there. Then our term, our dl by dwi term looks somewhat like this. dl by dy cap, dy cap by dh3, which is the constant term we know. Okay, so here we are having 100 timestamp, right? So this will be 100 dh100 by dh99. Like this, we will be having dh1 by dwi 100 I. So this will be the equation, or this will be the term, sorry, this will be the term for our 100 equation, for our 100 timestamp. That is, this will be the term for the oldest input. This will be the term for the oldest input. Here we have seen this is the term for the oldest input for the 3 timestamp. So this will be the term for the oldest input for 100 timestamp. Here again, if we consider this as a constant, which is c, then what we are doing, we need to multiply this dh, the hidden state derivative, which is 0.7 100 times, like this. Just imagine how small this number will be. This number will be nearly equals to 0. Here we don't even need to go to the 100 timestamp. From the 20-30 timestamp, we can observe a value which is near to 0. That is, the contribution of that input, which will be the earliest input or the older input, will be 0, nearly 0 in predicting the outcome. So what is happening here? Here now, if we take the 100 timestamp, what is happening in this term? In this term, in this gradient term, our gradient is becoming 0. That is, the contribution of this gradient, contribution of this part of the gradient is 0. That is, this part of the gradient is vanishing. So this term of the gradient is represented by whichever input will be 0. The contribution for that input in predicting the outcome will be 0. This is what we call vanishing gradient problem. And we can only observe this vanishing gradient problem for longer sequences, for the earlier inputs. This is what we have seen when we are discussing this example. This Python is the oldest or the earlier input. So its memory, its gradient became 0. So its contribution in predicting the outcome, which is the next word in this case, will be 0. This is how RNN forgets the memory of the earlier timestamp because of the vanishing gradient problem. I hope vanishing gradient problem is clear. Let's move on to exploding gradient part. So what happened in exploding gradient? Previously we have seen in vanishing gradient, some of our gradient terms were becoming 0. The gradient terms corresponding to the earlier input were becoming 0. That is, their contribution in predicting the outcome were becoming 0. In exploding gradient, just opposite thing will happen. The gradient term corresponding to the older or the earlier input becomes infinite. Why is it so? It happens because sometimes we use different activation function. Say instead of 10h, we are using ReLU. Then what will happen? Here, the derivative of the hidden states will increases as we move to the more and more older or earlier state. It increases as we move more and more to the older or earlier inputs. It increases exponentially. And for the oldest and for the earliest input, say for the timestamp t equals to 100 or more than 30-40, this terms becomes infinite. Due to this, our change in loss with respect to change in input becomes infinite, or change in loss with respect to change in hidden weight becomes infinite. Due to this, the weight updation will not happen for this two weights, and this causes unstable training. This exploding gradient thus causes unstable training. So this was about exploding gradient problem, which causes unstable training. So this was about today's video, where we have discussed vanishing gradient and exploding gradient problem. Now one can ask how we can solve these problems. Is there a solution for this? The answer is yes. There are solutions for this. Solution are, first is, we can reduce the problems that are facing with the RNN by using different activation functions. This will be not that effective, but it will reduce the problems that we are causing with RNN. Second is to just move to different architecture, which are LSTMs, transformers, etc.